studies on this misalignment and spirals, and hopefully you will still find it interesting and relevant. The background image you are seeing in here is a synthetic observation of a misaligned simulation, misaligned disk simulation. The inner and outer disks are misaligned, and the inner disk casts a shadow to the outer disks. The reason I choose this image is that this looks like an eye to me. So hopefully simulations could also be another sharp eye for us to understand the universe. So we have seen a variety of disk structures like gaps, spirals, and crescents. Although these structures are seen at the outer disks, they should also be seen at inner disks because the physics is the same. We have seen multiple gaps and rings. Some rings are misaligned, like in GW Ori system. The innermost ring even have an eccentricity. And we have also observed planets within some of the rings of the cavity. We have also seen spirals and crescents. The spirals have been observed at both submillimeter and near infrared, while crescents have also been seen in submillimeter and near infrared. So besides these disk features, there's another disk feature which is more unique. It's uniquely being seen in near infrared and optical observations. These are disk shadows. So besides these nice spirals in HD 142527, we have also seen these dark lanes at the cavity edge. And this is best explained by misaligned inner disks. So the inner disks cast a shadow. The inner disk block the central star at the node position and cast a shadow to the outer disks. And the width and the shape of this shadow sensitively depends on the inner disk geometry and the inner disk thickness. So by studying these shadows, we could constrain the inner disk size and the inner disk misalignment angle. So in my talk, I'll mostly focus on these spirals and these shadows because these are most prominently seen in near infrared and optical. So all of these are observations for the spiral systems, except the lower right one, which is observed at submillimeter. All of these spirals have been observed at near infrared. And some of the spirals are very regular, like these two spirals, while some spirals are very chaotic or complicated. And if you look at these spiral systems, a lot of them actually have shadows with them. Like all these four of them, they have discontinuity, have shadows, suggesting there is a misaligned inner disks. If you look at all of these spiral systems at AMA wavelength, you will find that more than half of them actually have this crescent structure in the AMA image. Right? So overall, it seems that the spirals, the misalignments, and the crescents, and the cavities are normally occurring together. So something is going on in these systems causing all these features. So one mechanism to explain most of these features is that you could have a giant planet or companion in the disk which breaks the disk. So this is what I'll talk first about the disk misalignment and shadow. Then I'll talk about spirals, focusing on spirals excited by eccentric perturber. And then finally, giving some theoretical argument on how to form planets at early stages. So the easiest way to cause misalignment is that you have a massive companion in the disks, and this companion is misaligned with the disk, and the companion carves out the deep gap in the disk. And because they carve out deep gap, the inner and outer disks now do not communicate with each other, so they could precess by themselves. So after a while, the inner disk could precess 180 degrees, and then it will cause this large misalignment between inner and outer disk. Okay. So most previous studies on misalignment, on misaligned planets focused on planet migration or the planet's inclination change. Very few works focus on the disk's response to this companion in the disks. And most of the simulations on this line of work is SPH simulations. So these simulations have normally apply a relatively large alpha. So in here, you normally have a disk warping. So the disk has a mild warp in the disk, while this whole, both inner and outer disk process as a whole. Okay, they process at the same speed. So you won't develop a large misalignment. As we know, protoplanet disk has relatively small viscosity, small alpha. So we want to study how small alpha disks could lead to disk breaking. So this is a simulation, Athena++ simulation with mesh refinement with a misaligned planet. The planet is still at the mid-plane of the computation domain, while the disk is misaligned. So here you can see the planet open a gap, and the inner disk process causes large-scale misalignment. So let's watch some movies on this type of simulation. So here we have a mildly inclined giant planet. And here the disk has a large viscosity, is alpha 0.01. So then you can see that the planet tries to open a gap, but the gap is not deep enough so that the inner and outer disk are still connected. So the inner disk tries to process, but they stuck with the outer disks. Eventually the disk develop a mild warp, and this whole disk process as a whole. So if we carry out the same simulation, but decrease the viscosity by a factor of 10, then the planet opens a much deeper gap, and then the inner disk process at this precision frequency. Eventually, it could lead to a much larger misalignment between the inner and outer disks. So here you can see that the disk breaking is closely related with gap opening process. If a deep gap can be opened, then the inner disk and outer disk could disconnect with each other, and eventually you could develop a large misalignment, a twist in the disks. So theoretical studies suggest that the disk breaking condition is like this. So overall, even with a very small alpha or very thin disk, you still need a relatively large planet or large companion to break a disk, cause misalignment. So a massive planet is still needed to break disk, and this will naturally explain why we have seen these shadows in these transitional disks with large cavities. And these normally have spirals and also have vortices. These can all be tracked by this companion in the disks. And this also suggests that the disk with shadows could be the prime targets for searching exoplanets in disks. So to demonstrate that all these features could exist together, this is a synthetic observation from these misaligned disk simulations. And you can see this shadow in the vertical direction. You can see the vortex, and you can see the spiral. And this spiral will move, orbit around the central star. This vortex will orbit around central star at Keplerian speed. So they will across this shadow. So then the shadow will cut this vortex into two. So this is like these observations. You have a shadow here. And if you look at the temperature in the shadow is colder. This is because it's in the shadow, so it's cold. And this has been seen in AMA observations for HD 142527. You have this vortex, the cut by this shadow, and the temperature in the shadow is lower. So because we are doing these simulations, we could also track how these shadows changes with time. And then we find that the shadow not necessarily move at the same speed as the inner disk process. Like among these two snapshots, the inner disk has precessed for 60 degrees, but the shadow has only changed for 30 degrees. And this turns out is to be a geometric effect. And this is best demonstrated by a model, but it's just a toy model. I have outer disks by the paper, and I have an inner disks misaligned, and the inner disk angular momentum vector is here. And the inner disk will precess around this axis. So in this geometry, you can see that, so I need to point out that these two dark regions here point out to where the shadow will be. So in this geometry, the shadow will circulating around the central star. The shadow will move at the same speed at the inner disk precess. Okay. But for different geometry like this, then the shadow will not move, almost not move at all. While the inner disk precess, the shadow will basically vibrate back and forth. Okay. So the speed of this shadow movement and the speed of inner disk precession is related to with this formula. So in future, if we can detect the shadow's movement in the disks, either it's inner disk or outer disk, we could use these shadows movement to constrain the inner disk precession angle or the inner disk geometry or potential companions orbits. So this is about the disk misalignment. And then I want to talk about how the spirals can be excited by planets. So we have seen these spirals at the outer disks. Some are very regular, like this m=2 spiral. And some spirals are very chaotic, like these. So what causes the difference between a smooth spiral like this and very chaotic spirals like this? So before we talk about the theory, let's first look at some fundamentals, why we have spirals in disks. That because the wave propagation in a disk has to be in this spiral form. Like if we have a static water pond and we perturb the surface of the water pond, like we draw pebbles, then we excite these ripples, right? These are spherically propagating ripples. But in a Keplerian rotating disk, if you do the same thing, the perturbation will quickly become a spiral shape. This is because the perturbation will first orbit around the central star at Keplerian speed, and then the propagation will propagate in and out at some speed. But due to the Keplerian shear, these waves will quickly be sheared into spiral form. So no wonder we have spirals in disks, because this is the only form allowed in disks to propagate. Okay. So if we have a circular moving planet, and we are in the rotating frame of the planet will excite these spirals. And these spirals will, when the planet moves around the central star at Keplerian speed, it will excite the spiral all the time, and all the spirals will interfere with each other at same position and form this nice steady spiral arm. So this spiral will co-rotate with the planets at the local Keplerian speed. But if the planet has some eccentricity, so even if we are in the co-rotating frame of the planet will still move in and out from semi-major and semi-minor axis. So in this case, the spiral will be very dynamic. The waves won't be interfere with each other perfectly. So you will see that some of the waves will intersect with each other. Sometimes it will look like the spiral bifurcates, like these. Spiral bifurcates like these. Okay. So it's never steady. Okay, so the spiral never steady, and you could even develop an analytical theory to explain that. Basically, it's similar to if you have a boat moving in a water or airplane flight, then at the boundary of all the waves, you will form the wake. So you could develop an analytical theory and explain all the observations. So nevertheless, the bottom line here is that as long as the planet has some eccentricity, a mild eccentricity, the planet will generate a spiral feature, which is very different from a circular planet. So here is the spirals excited by eccentric 0.2 planets, and every spiral is labeled with the same color dots. And you can see there are more than 4 spirals excited by the planet. And the pitch angle of all the spiral is very different from the spiral from the spiral of a circular planet. And these spirals are not moving around the central star at the planet's Keplerian speed. Instead, they have a variety of pattern speeds. Right? So the spiral could move faster or slower than the planet's orbit around the central star. So it's highly dynamic. So these spirals is very complicated. These are very complicated. They may be able to explain these complicated spirals observed in some of these systems. there are recent work suggests that even with these regular spirals, m equals 2 arm spirals, you could already have an eccentric planet in the disks. And this eccentric planet can excite these spirals, explaining these observations. So one very promising way to move forward by studying these spirals is that we can study how the patterns of the spirals changes with time. So in this study, she et al. Find that these two spirals in these systems actually move at different speed. Just by using the data 1 year apart, they find that one of the spiral seems to not move at all, while the other spiral seems to have some notable change over this 1 year period of time. So by studying these spirals pattern change, potentially we could constrain planets' eccentricity in these disks. So, so finally, the last 2 minutes, I want to talk about how these spirals may help us to understand planet formation in these young disks. So far, we have two different planet formation models. The first is core accretion model. So the planet builds a core, and then the core will gather atmosphere and eventually run away accretion. And this model is good in a way that it could happen anywhere, at both inner disks at 0.1 AU or at outer disks at 50 AU. But the problem in this traditional core accretion model is that it will take a long time for this core to gather atmosphere and to run away. This is more than 1 million years. So while at the same time, we have seen a lot of protoplanetary disks with substructures at a very young age. So how could planets form at a very early stage? So a competing model is this gravitational instability model. So in this model, the planet could form very early because the disk can be gravitationally unstable at early stages. But the drawback of this model is that these disk fragments will only happen at outer disk, where the disk cools fast enough. This normally happens beyond 50 to 100 AU. So this model will not be able to explain planets formed very close to the central star. So could there be a third model, or could be there some hybrid model that you have these spirals, and these spirals do not fragment, but they could concentrate dust particles enough to form planetary cores. Okay. So this is what we studied recently by studying the spiral structures in self-gravitating disks. And we noticed that a lot of angular momentum transport in self-gravitating disk is through these spirals. Very little angular momentum transport is through the disk turbulence. So the disk is very weakly turbulent, and the dust could settle significantly in these disks. So in this simulation, recent simulation with my postdoc, Hans Bayer, we have dust particles in 3D self-gravitating disk simulations. And these dust particles settle significantly at the disk midplane. And by marrying the alpha responsible for accretion and alpha responsible for dust settling, we find that the alpha responsible for accretion is 1 or even 2 order of magnitude higher than alpha for dust settling. So dust is highly settled in these self-gravitating disks. And these dust also concentrate in these spirals significantly. You will think that the spirals will not be able to concentrate big particles because big particles do not feel aerodynamic drag from the gas. But big particles also feel the gravity from the gas spiral. So if we include gas gravity to dust particles, we see these spirals can concentrate dust particles. So you could work out the drag force and gravitational force. So overall, when the particle Stokes number is larger than 2 Mercure parameter, the gravity from the gas could concentrate dust particles. So all size particles can be trapped in these self-gravitating spirals. So eventually put everything together, we have 3D gravitational instability simulations with dust particles with dust to gas feedback, and the disk does not fragment into gaseous clumps, but these dust particles is concentrated in these spirals significant enough that they form bound planetesimal planet embryos. So eventually, in these simulations, we see that the maximum clumps, the dusty cores we get is around 10 Earth mass. So this suggests that planet embryos or low mass planets can form very early in these graphene-inspired spirals. The graphene-inspired spirals do not need to fragment to form planets, while the particles could concentrate enough to become bound objects. Okay. So that's all. In my talk, I talk about how a companion could break the disks, and you really need a massive companion to break the disks and causes disk misalignment. And the shadows will change with time, but the shadow may not move at the same speed as the inner disk precision. The spirals can be highly complicated. So as long as the planet has some eccentricity, the spirals will be very different. They will be very dynamic. And finally, the spirals in graphene unstable disks could concentrate particles and eventually form planets early. So the final note is that when we start to probe the inner disks, the structure's time evolution will give us a totally different dimension to constrain planet formation more than disk study. And the orbital timescale will not be the only relevant timescale. You could have the disk precision timescale or the spirals dynamical timescale. Okay, so that's all. Thank you.
Many thanks for this very interesting talk. Any questions from the hall? And then maybe from online, if there are some questions. There is an online question, I think.
Yes, concerning the eccentric planets causing the irregular spirals, I'm wondering if due to the interaction with the disk, the planet will actually be made less eccentric and finally go into a circular orbit. So in that sense that this will only be, I don't know what timescales are involved, but this would be only part in an evolutionary stage of the thing going to a regular orbit.
Yeah, so in a traditionally planet interaction model, that's indeed true. The planets will become circular orbit over the circulation timescale, which is normally comparable to the migration timescale. However, recent studies have suggested that if you include the planet's radiation, the planets have irradiation to the disk, that co-rotation torque will drive the planet eccentricity. So the planet not necessarily will be circularized. Instead, the eccentricity can grow high. How high it can grow, it's a problem. It's still people not sure, but current simulation suggests it's around 0.1. Eccentricity could reach 0.1. And for a massive planet, the picture is more complicated because a massive planet will open a gap, and then the planet will interact with the gap, and you will have eccentric resonances. Then the planet eccentricity could theoretically go even higher. So for both low mass planet and high mass planets, recent studies seems to suggest that eccentricity will not be really zero. It could be like 0.1, 0.2. It may not be like 0.5, but it will still could be large enough to be noticeable. Yeah.
Thank you. There is another question from John Monet, who is interested whether is there any way to generate very small structures in the inner dust rim, or only large-scale vortex symmetries are possible?
Yeah, so for the inner dust ring, the simulations by Mario Floch suggest that it's likely to be a large-scale vortex, and I think that's generally true. When you have accretion changes, accretion rate across a radial distance, a short distance, you will pile up material, and then you will form a density ring, and this density ring will break into vortices. And the vortices may not be necessarily a single vortex, so that may be a little bit different because the vortex formation depends on the disk's H/R aspect ratio. At the inner disk, the aspect ratio is smaller, so the vortex you may see like have a 2 or 3 vortex form at the beginning, and they will merge. Whether they will eventually become one single vortex, it's not very clear. But generally, if you have density ring, it will form a vortex. Yeah, so I think it will be a large-scale vortex.
Okay, thank you. Any question?
Another question by Ellen.
That is a question. Average is interested if you have thought about how the star's axis of rotation would change in your disk braking scenario. So how the star's axis of rotation would change.
The star, you mean the star torques the inner disks, or is that the question?
How the star's axis of rotation would change in your disk braking scenario.
The axis, the star's axis, right? Yeah, so in here, I do not consider the star and the disk interaction. I only consider the misaligned planets and the disk interaction. So if you consider the stars and disks interaction, then you have the magnetospheric accretion. And if the magnetospheric accretion, the magnetosphere give enough torque to the inner disk, which is similar to the planet, which can give a torque to the inner disk, it could still break the disk if they are significantly misaligned. But I think this needs to be simulated in MHD simulations. So I don't have a clear answer to that. But generally, if you have a torque in the disks, which is not coplanar, you will break the disk.
Okay, thank you. Let me have a more general question that all these disks what you showed at the beginning with the shadows and spirals, these are those famous large disks. And from ALMA now we know that most of the disks are actually small, boring, much more less interesting disks. Mm-hmm. So can you scale down your whole picture for this small disk, or they simply don't produce big enough planet to show it?
Mm-hmm. Yeah, so if we go to lower mass range, we have seen, as we have heard in Evan's talk, it become more ring-like instead of a spiral-like or vortex-like. Most of the vortex shadow and spiral are observed for very large disks, and even the star is more than 2.5 solar mass. So for the inner disks, I would feel it will be more like a ring structure, but it all depends on the planet mass. If you have a Jupiter, for example, if you have a Jupiter or hot Jupiter at the inner disks, that hot Jupiter will do the same thing. It will excite very strong spirals. It will causes vortex at the gap edge, open a very wide gap. So the physics, I think, is the same, and especially at the inner disk, when the disk is thinner, the gap opening is much easier. So the gap opening planet mass is related with h/r to the 5th power. So at the very inner disk, when the disk is thin, you don't need Jupiter to open a cavity. You only need several Earth mass or Neptune mass planet to cavity. So in this sense, it's even easier to have structures at the inner disk, especially regarding gaps.
Okay, thank you very much. So let's thank Zhaohuan again.